Good afternoon. My name is Rob Harrison, and I'm going to tell you today about a way to detect network-wide heavy hitters with perfect accuracy and low communication overhead. While network switches process packet flows all the time, we're usually most interested in those flows that are heavy hitters. That is, those flows defined as sets of similar packets grouped by a single header or headers, such as a 5-tuple microflow, or just simply a destination IP address, that exceeds some threshold on packet count or bytes. In this table, we see that of the 3 packet flows depicted on this slide differentiated by color, the green flow is the heavy hitter. Detecting heavy hitters is important because their presence could indicate conditions that require immediate attention, such as attack, misconfiguration, or failure. Detecting heavy hitters on a single switch is itself challenging because we have to fit the data structures and perform the computations to calculate these heavy hitters on network switches, which are significantly constrained in both memory and computation. Detecting heavy hitters on a single switch, given these constraints, has been the focus of much prior work. But in reality, our networks consist of far more than a single switch. And to diagnose some problems like denial of service attack or TCP incast, just performing single switch heavy hitters at each location won't suffice. Consider the case where we want to detect all flows that exceed some global threshold, whether it's on packet bytes or counts. And let's say that this blue flow is split across 3 ingress switches. If we counted this flow at each switch, the count at any one switch may not exceed the target threshold. But in total, this flow far exceeds the threshold from a network-wide perspective. In order to determine if a flow exceeds a global threshold on a network-wide basis, we must introduce some coordination among the counting switches. A strawman solution might send all the packets of a flow to be counted at a central collector. By processing all the packets of a flow, the collector will be able to accurately count the flow, but this method quickly overwhelms the central collector under any real load monitoring multiple flows. In order to accommodate higher data rates or monitor several flows, one might sample the original flows at some rate, such as 1/n packets, and reducing the number of packets sent would avoid crushing the collector, but at the cost of decreased accuracy, especially on short time intervals. So these 2 approaches show that there is an inherent trade-off between the coordination and accuracy. And so since we must perform this coordination for each flow to be monitored, how can we achieve high accuracy with low coordination? Well, we can reason about the amount of coordination required to achieve accuracy in the context of the distributed continuous monitoring problem. This is a general monitoring problem to which network-wide heavy hitters can be reduced. In the problem, we have N switches that are forwarding packets. A central coordinator tries to determine when a global threshold, tau sub g, has been met for some flow by listening to reports from switches. These switches maintain a current count for each flow and report to the coordinator when this count meets the local threshold, tau sub L, at each of the switches. After receiving some number of reports from the switches, the coordinator determines that the flow has exceeded the global threshold. And a number of ways exist to combine local thresholds and reporting conditions that are both inaccurate and inefficient. But the best known deterministic solution to this problem that maintains 100% accuracy, we call the CMY upper bound. And in this technique, we proceed with a fixed series of rounds. And in each round, the local threshold is set as a function of the global threshold divided by the number of sites and the current round. So if we consider a case where there are 4 total switches and a global threshold of 64, this would result in 4 rounds with each of the local thresholds in the round shown in this table. So the way this would work is in the first round, all local thresholds are set to 8. After the coordinator receives N reports from the switches, it would send a message to all of the switches to advance their local threshold to the next round. When the coordinator receives the last report in the last round, it determines that the global threshold has been exceeded. Now this approach has provable upper bounds to achieve 100% accuracy, but the question we ask is, can we do any better? And we think we can. So in order to better set local thresholds, we can exploit the property of spatial locality in networks. If we look at this topology, we see that external traffic enters this network, this notional data center network, from only one of a few external ingress locations. Similarly, internal traffic enters the network from only a few ingress points as well, and both of these are fewer than the total number of switches in the entire network, which, as you recall, is a factor in determining local thresholds for the CMY upper bound. And the precise distribution of flows across these ingress points can change over time, but often at much longer timescales than the intervals at which we like to perform heavy hitter detection. So if we can adapt the local thresholds for flows at each switch that exhibit locality, we can reduce the coordination overhead without sacrificing accuracy. And so to do this, we modify the CMY approach just a bit. So we adapt the local thresholds to account for this locality. So rather than proceeding to update local thresholds in a fixed sequence of rounds, we'll continuously update local thresholds over successive time windows of a specified duration. And so assuming that we don't know anything about the distribution of flows among the switches a priori, we start with the local threshold set as a fair share of the global threshold. If we do have prior knowledge of the flow distribution across the switches, we can start with better tuned local thresholds. This information would improve our approach, but it's not required for correctness. And so when the count at a switch exceeds the local threshold, it generates a report to the coordinator. The coordinator maintains an estimate of the global count, and it updates this estimate whenever it receives a report from a switch. In the absence of a report from the switch, the coordinator overestimates and assumes that the current count of any non-reporting switch is local threshold -1. When the coordinator's estimate exceeds the global threshold, it polls the other switches, which reply with their true count. These true counts and subsequent true count reports allow the coordinator to calculate an exponentially weighted moving average, or EWMA, for each switch over time. With this information, the coordinator can then adjust local thresholds as that switch's fraction of the global count. And so by using the EWMA as part of the local threshold, we do two things. We increase the flow, or we increase the thresholds where the flows are heavy, and this reduces the number of reports sent to the controller or the coordinator. We also decrease the thresholds whenever the flows are not heavy, which allows us to maintain the accuracy in the face of unexpected counts at other switches. And both of these processes are continuously occurring over time. So we created a prototype solution that implements the switch-level logic in approximately 200 lines of P4 code for both the VMV2 and Tofino targets. To evaluate this technique, we ran heavy hitter queries for the heavy 5-tuple flows from network traces. And we used real-world packet traces from Qizhe that consisted of 64 million packets per minute and about 6.4 million packets per monitoring interval. But because this data set consisted of traces from a single point-to-point link, we simulated a one big switch network by assigning each source in the network trace to some ingress switch with a variable probability. We then calculate the coordination overhead in each experiment and compare to the CMY upper bound while varying a few key parameters. This table summarizes the results for these two parameters, or for two of these parameters. Regardless of the global threshold we chose, ranging from 200 to 1,000, we saw a 60 to 70% reduction in the communication coordination required to the coordinator. As we increased the number of switches from 2 to 20, this effect became less pronounced, but still at up to 20 switches, we still saw 30% reduction in the communication overhead. So in summary, I presented a network-wide heavy hitter detection scheme that uses adaptive thresholds to reduce the communication overhead while maintaining high accuracy. So in future work, we'd like to explore how to better scale to a larger number of sites, perhaps by incorporating some probabilistic reporting techniques, but while still without sacrificing any accuracy. We'd also like to improve the switch-level memory efficiency of our approach by filtering out mice flows with approximate data structures and only storing the per-flow state for those potential heavy hitters. For more details, please check out our paper or come talk to myself or my co-author, Qizhe, who's in the back, who's also here. Thank you very much, and I'm happy to take your questions.
So a minor clarification question.
Sure.
I think I missed a slide where you talked about the actual accuracy, because I know you were doing some estimates and using estimated weighted moving average, but I didn't actually think I saw the slides with that.
So I led with, I maintain perfect accuracy and low communication. So we don't sacrifice any accuracy. The estimate is just a tool to reduce the number of times we actually pull for the true counts from the distributed switches, which actually is kind of a liability in our scalability as the number of sites grows very large. So that's the balance that we're trying to get right in future work. But we maintain perfect accuracy. We have no issues with either precision or recall in all our experiments.
Okay.
Another clarification question. So in your example, you show that there is a flow that enters via multiple points, and then you said that you have to go like distribute it. But isn't there like some fanning in at some point, and the flow is going to one destination somewhere in the network? So at some point, if there are like even like 10 different ingresses that are sending to that destination, the switch which is connected to the destination should actually see the heavy hitter, right? So I'm wondering why the problem appears. Is it because you're assuming that there are like different egresses, so exit points, and that it's also distributed? And so that's what I'm missing, I guess, in your talk.
So I think it's highly topology dependent, the answer to your question, whether or not a single switch will see all of the packets for a given flow and precisely how you define a flow for that query. So this is a general approach for a flexible definition of flow that could possibly egress and ingress multiple locations, as well as any other unforeseen circumstances that we didn't account for. So I agree that if there is a single switch that will see all of your packets for a given flow, it can be better to put them all there. So when the number of switches that monitor is 1, there's no problem with accuracy, but that's not always practical, and it's not always, won't always be able to fit all of the counters for all of the flows on the one switch.
I guess one use case could be in an ISP, right? You can have multiple ingress router and different egress as well, and then I guess you try to compute the heavy hitter prefix instead of like flow, but
right.
Yeah. Jen knows. So.
All right, let's thank our speaker one more time.